Microservices Demystified, a beginner's guide to modern software architecture. Chapter 1, The Evolution of Software Architecture, from Monoliths to Microservices. Imagine for a moment you're building your dream house. Before the first brick is laid or the first nail hammered, you'd spend countless hours with an architect, meticulously planning every detail. The layout, the wiring, the plumbing, how sunlight will fill the rooms. This intricate blueprint isn't just about aesthetics. It's about functionality, durability, and how well the house will serve your needs years down the line. It's about making sure your home can adapt as your family grows or technologies change, without requiring a complete demolition and rebuild. In the world of software development, architecture serves a remarkably similar purpose. 1.1 What is software architecture? At its heart, software architecture is the blueprint for a software system. It defines the high-level structure, outlining the major components, their responsibilities, how they interact, and the principles that guide their design and evolution. Just like a house blueprint, it's not concerned with the finer details of individual bricks or tiles. Those are handled by the builders, or in our case, the individual software developers writing code for specific features. Instead, it focuses on the foundational framework that holds everything together. Why does this matter so much? Because a well-thought-out architecture can mean the difference between a system that scales effortlessly, adapts to change, and remains easy to maintain, versus one that becomes a tangled mess, prone to errors, and prohibitively expensive to update. Software architecture profoundly impacts scalability. Can the system handle more users or more data without collapsing? Maintainability. How easy is it for developers to understand, fix bugs, and add new features? Cost. What are the long-term expenses in terms of development, infrastructure, and operations? Development speed. How quickly can new ideas be turned into working software? Resilience. How well does the system cope with failures without crashing? Over the decades, as technology evolved, so too did our approach to software architecture. Early computing systems were often monolithic, tightly integrated units tied to specific hardware. As applications grew in complexity, and the internet era demanded ever more flexible and scalable solutions, the limitations of these traditional approaches became apparent. This journey from simpler, tightly bundled systems to highly distributed and specialized ones is the story of modern software architecture. And it's the story we'll explore in this chapter. 1.2 Understanding the monolithic approach. Pros and cons. For many years, and still in many cases today, the dominant architectural style for building enterprise applications has been the monolith. A monolithic application is built as a single, indivisible unit. Think of it like that all-in-one kitchen appliance. It's a food processor, a blender, a juicer, and perhaps even a coffee grinder, all housed within one casing. All the different functions, handling user requests, processing business logic, interacting with the database, managing user interfaces, are contained within one single application process. When you want to deploy a monolithic application, you package the entire system as one large executable file or web archive and deploy it as a single unit. All features from customer management to product catalog to order processing reside in the same codebase. The appeal of the monolith, its advantages. The monolithic approach isn't inherently bad. In fact, it offers several compelling advantages, especially in the early stages of a project. Simpler initial development. Starting a new project as a monolith is often straightforward. There's no need to worry about complex communication patterns between services or distributed data. All code lives together, making it easier for a small team to get off the ground quickly. Easier testing. Since all components are in one place, you can conduct end-to-end tests more easily. Imagine testing all the features of that single kitchen appliance by just plugging it in and trying them out. Unified deployment. There's only one artifact to deploy, one set of processes to start. This simplifies operations initially, as you don't need to coordinate multiple deployments. Simplified debugging. When an issue arises, all relevant code is typically within the same process, making it easier to trace problems using standard debugging tools. When monoliths become monsters. The disadvantages. While the initial benefits are clear, the monolithic approach can quickly turn into a significant liability as the application grows larger and more complex. This is where the concept of monoliths becoming monsters comes into play. Consider the once booming tech company, SpeedyShip, a fictional overnight delivery service. They started with a small, monolithic application handling everything from package tracking to billing. In their early days, this system was highly efficient. But as their customer base exploded and they added new services like international shipping and drone delivery, their monolith became unwieldy. Here's what SpeedyShip, and many companies like them, discovered about the downsides of the monolithic approach. Scaling challenges. If one part of the application, say the package tracking module, experiences a sudden surge in traffic, the entire monolithic application must be scaled up, consuming more resources, CPU, memory, even if other parts of the application, like billing, are barely used. This is akin to buying a completely new, bigger all-in-one kitchen appliance just because you need more blending power, leaving the juicer and food processor capabilities largely unused. Slower development and deployment. As the codebase grows, it becomes harder for multiple teams to work on different features simultaneously without stepping on each other's toes. Building and testing the entire application takes longer. For SpeedyShip, a simple bug fix in the shipping label generator meant recompiling and redeploying the entire billion-line codebase, an operation that could take hours, sometimes even days, leading to significant downtime risks. Technology lock-in. It's difficult to adopt new technologies or languages for specific parts of the application without rewriting the entire monolith. If SpeedyShip wanted to use a modern, faster database for their package tracking, they couldn't just swap it in. It would require a massive overhaul of the entire system. Reduced resilience. A single fault in one component can bring down the entire application. If SpeedyShip's billing module had a memory leak, the whole tracking and customer service system would cease to function, potentially leaving thousands of customers unable to check their critical package deliveries. High barrier to entry for new developers. Understanding a massive, interconnected codebase takes a long time, making it challenging for new team members to become productive quickly. Fear of change. Due to the tightly coupled nature of monolithic code, even small changes can have unexpected, cascading effects throughout the system, leading to developers being hesitant to make necessary improvements or fixes. These challenges led the software industry to seek new architectural paradigms, pushing towards more modular, flexible, and resilient systems. 1.3. The rise of distributed systems and the need for chain. The shift away from the monolithic approach wasn't a sudden paradigm. It was driven by several powerful forces that reshaped the requirements of modern software. The Internet age and global scale. The advent of the Internet transformed software from local, desktop applications to global, always-on services. Users expect applications to be available 24/7 from anywhere in the world and capable of handling millions of simultaneous requests. This demand for massive scale and high availability stretched the traditional monoliths to their breaking point. Cloud computing. The rise of cloud platforms like Amazon Web Services, Microsoft Azure, and Google Cloud Platform provided unprecedented access to flexible, on-demand infrastructure. Instead of buying and maintaining physical servers, companies could rent computing power, storage, and networking resources as needed. This offered the perfect environment for deploying smaller, independent software components. Rapid iteration and business agility. In today's fast-paced market, businesses need to be able to respond quickly to new requirements, launch new features, and pivot strategies based on customer feedback. The slow, cumbersome deployment cycles of monoliths became a major impediment to this agility. Specialized services and diverse technologies. As applications become more complex, different parts might be best built with different technologies. A reporting module might benefit from a powerful data analytics engine, while a real-time chat feature requires a high-performance messaging system. Monoliths make it difficult to mix and match these optimal technologies. Team autonomy and organizational structure. Large monolithic applications can become bottlenecks for large development teams. Often, different teams need to work on the same codebase, leading to coordination overhead and reduced independence. There was a growing desire for architectural styles that empowered smaller, cross-functional teams to work more autonomously, deploy independently, and take full ownership of specific parts of the system. These drivers collectively created a demand for an architectural style that could address the scalability, flexibility, resilience, and agility requirements that traditional monoliths struggled to meet. This demand paved the way for the emergence and popularization of microservice architecture. 1.4 Introducing Microservices, a high-level overview. Against this backdrop of evolving needs and technological advancements, microservice architecture emerged as a leading solution for building complex, scalable, and resilient distributed systems. At its core, a microservice architecture structures an application as a collection of small, autonomous, and independently deployable services. Think back to our kitchen appliance analogy. If a monolith is an all-in-one machine, a microservice architecture is like having a kitchen full of specialized tools. A dedicated blender, a powerful food processor, a standalone coffee grinder, and a separate juicer. Each tool does one job, and it does it exceptionally well. You can upgrade just your blender or replace your coffee grinder without affecting any other appliance in your kitchen. Let's break down the key characteristics of what defines a microservice. Small and focused. Each microservice is designed to do one thing and do it well, typically representing a single business capability, e.g., a customer service, an order processing service, a product catalog service. The definition of small isn't about lines of code, but about focus and responsibility. Autonomous. Each service is designed to be self-contained. It operates independently, owns its own data, and manages its own lifecycle. This means it can be developed, tested, and deployed in isolation from other services. Independent deployability. This is a crucial practical benefit. Because services are autonomous, you can deploy updates to one service without needing to redeploy the entire application or impacting other services. If Speedy Ship used microservices, a problem in their billing service wouldn't affect package tracking or customer service. Only the billing service would need to be updated and redeployed. Communication via APIs. Microservices communicate with each other over a network, typically using lightweight mechanisms like application programming interfaces, APIs. These APIs act as contracts, defining how services can interact without knowing the internal workings of another service. Run in their own processes. Each microservice runs in its own process, isolated from others. This provides fault isolation. If one service crashes, it doesn't take down the entire application. The adoption of microservices isn't a silver bullet, and it introduces new challenges, which we will explore throughout this book. However, the benefits they offer in terms of scalability, resilience, technology independence, faster deployment cycles, and enhanced team autonomy have made them a cornerstone of modern software development for organizations seeking to build robust and agile systems at scale. This chapter has laid the groundwork by understanding the architectural landscape and the motivations behind the shift to microservices. In the next chapter, we will dive deeper into the core concepts that define these independent, specialized building blocks of modern applications. Chapter 2, Core Concepts of Microservices, What Makes Them Tick? In the previous chapter, we introduced microservices as a modern approach to building software, moving away from monolithic designs to embrace smaller, independent units. But what truly makes a piece of software a microservice? It's more than just being small. It encompasses a set of core principles that define how these services are built, interact, and operate. Understanding these foundational concepts is crucial before attempting to design or work with microservice architectures. 2.1 Defining a microservice. Small, autonomous, independent. While the micro in microservices might suggest size, it's not simply measured by lines of code or the number of developers on a team. Instead, it speaks to the scope of responsibility and the operational characteristics of the service. What does small truly mean? Small, in the context of microservices, refers to a focused, single purpose. A microservice should be functionally cohesive, meaning everything within it contributes to a tightly defined business capability. For example, instead of a vast user management module that handles everything from registration to profile updates, password resets, and subscription management. A microservice approach might decompose this into a user registration service, a user profile service, a password reset service, a user subscription service. Each of these services would be small in the sense that its scope is narrow and its purpose is clear. This focused scope makes the service easier to understand, develop, test, and maintain. Autonomy, the power of self-sufficiency. Perhaps the most critical characteristic of a microservice is its autonomy. This means each service is designed to be self-contained and independent from others. An autonomous service owns its data. It manages its own database or data store. No other service should directly access another service's database. This is a fundamental principle to prevent tight coupling and allow services to evolve independently. We'll delve deeper into this in Chapter 5. Owns its logic. All the business rules and decision-making for its specific capability reside within the service itself. Decides its own technology stack. An autonomous service can be built using the programming language, frameworks, and databases that are best suited for its particular task, without imposing these choices on other services. This allows for technological diversity and the adoption of cutting-edge tools where appropriate. Manages its own lifecycle. From development and testing to deployment and scaling, an autonomous service can largely be managed independently by its dedicated team. This autonomy is empowering. It means a team building a notification service doesn't need to ask permission from the order processing service team to upgrade their database or switch their messaging framework. They are masters of their own domain. Independent deployability, the ultimate enabler. The ability for a microservice to be independently deployable is the practical manifestation of its smallness and autonomy. It means you can make changes to one microservice and deploy that updated service to production without redeploying other services. The rest of the application remains untouched and running. Coordinating with other teams excessively. While some coordination is always necessary, especially regarding API changes, the act of deploying a service update becomes simpler and quicker. Taking the entire application offline. This enables continuous delivery and deployment, allowing for rapid iteration and faster time to market. Imagine Speedy Ship from Chapter 1, now running on microservices. If they need to update the logic for how shipping labels are generated, they only update and redeploy the shipping label service. The billing service, package tracking service, and customer support service continue running uninterrupted. This dramatically reduces risk and accelerates the pace of innovation. Ultimately, independent deployability is what allows microservices to deliver on the promise of agility and quick response to business needs. 2.2 Bounded contexts, the key to service decomposition. One of the greatest challenges in transitioning from a monolith to microservices is deciding where to draw the lines between services. How do you decompose a large application into smaller, meaningful units? This is where a powerful concept from domain-driven design, DDD, becomes invaluable: the bounded context. A bounded context defines a specific part of a larger business domain where a particular model or concept, like customer or product, has a consistent meaning and is explicitly defined. Think of it as a logical boundary within which a specific set of terms, definitions, and rules apply. Outside that boundary, the same term might mean something entirely different. Let's use our Speedy Ship example. In the sales and marketing bounded context, a customer might primarily be defined by their contact information, marketing preferences, and demographic data. This is who we market to. In the billing bounded context, that same customer is defined by their payment methods, invoices, and payment history. This is who owes us money. In the logistics bounded context, a customer is primarily defined by shipping addresses and delivery preferences. This is who we ship to. While all these customers refer to the same real-world entity, their attributes and behaviors differ dramatically depending on which part of the business domain you're looking at. The critical insight for microservices is that each microservice should ideally align with a single bounded context. This ensures that the service is cohesive, owning its specific model of the domain, and that its scope is clear. If a customer service tries to manage both marketing preferences and billing information and shipping addresses, it quickly becomes bloated and loses its focus, heading back towards being a mini monolith. By using bounded contexts, you clarify service boundaries. It provides a mental model for identifying where one service's responsibility ends and another's begins. Reduce coupling. By ensuring that each service owns its distinct view of the domain, changes within one context are less likely to ripple through others. Enable domain-specific language. Each service can use terms and concepts that are precise and unambiguous within its own context. Understanding and correctly identifying bounded contexts is a fundamental skill for successful microservice design, paving the way for services that are truly focused and autonomous. 2.3 Single Responsibility Principle in Microservices. The Single Responsibility Principle, SRP, is a cornerstone of good software design, originally articulated for classes in object-oriented programming. It states that a class should have only one reason to change. Translating this to the world of microservices, it means a microservice should have only one business capability for which it is solely responsible, and thus only one reason to change. This means if you have a product catalog service, its reason to change would be a modification to how products are described, searched, or categorized. It should not change because of new requirements for order processing or customer notifications. Let's illustrate with an example. Violation of SRP, a single order service which handles creating new orders, processing payments for orders, sending order confirmation emails, updating product inventory, tracking shipping status. Every time there's a change to payment processing, email templates, shipping carriers, or inventory management, the order service would need to be modified, retested, and redeployed. This makes it a bottleneck and prone to errors due to frequent changes in unrelated areas. Adherence to SRP, microservice style, an order placement service responsible only for creating and managing raw order data, a payment service responsible for payment processing, a notification service responsible for sending emails, SMS, an inventory service responsible for product stock levels, a shipping service responsible for logistics. Now, a change to how payments are processed only affects the payment service. Updates to email templates only affect the notification service. Each service can evolve independently, leading to reduced complexity. Each service's codebase is smaller and easier to understand. Easier testing. You can test individual service functionalities in isolation. Improved maintainability. Changes are localized, reducing the risk of unintended side effects. Faster development cycles. Teams can focus on a single responsibility without interdependencies becoming a bottleneck. The SRP, when applied to microservices, is a powerful guide for ensuring that your services are truly micro in their scope and truly independent in their operation. 2.4 Data hiding and API contracts. Having services that are truly autonomous and implement the single responsibility principle requires a clear boundary between services. This boundary is primarily defined by data hiding and API contracts. Data hiding, encapsulation. In traditional programming, encapsulation means hiding the internal implementation details of an object or module and only exposing a public interface. In microservices, this principle is elevated to the architectural level. A microservice's internal data structures, databases, and implementation details are private and should never be directly accessed by other services. This is a critical rule. If Service A directly reads data from Service B's database, then any change to Service B's database schema would likely break Service A. This creates a tight coupling that defeats the purpose of microservices. Each service owns its data, meaning it's the sole authority for that data. Good practice. If the customer service needs to know a user's address, it must ask the user profile service for it, not go digging in the user profile service's database. Anti-pattern, multiple services sharing the same database. While technically possible with complex partitioning or views, it invariably leads to tight coupling and limits independent evolution. API contracts. The language of interaction. Since services cannot directly access each other's internals, they must communicate through well-defined application programming interfaces, APIs. An API acts as a formal contract between services. It specifies what operations a service offers. You can request order details. You can update an item's stock. What inputs it expects. The format of the data it needs to perform an operation. What outputs it will provide. The format of the data it returns to the caller. What errors it might return. How it communicates problems. Think of it like standardized plugs and sockets. A product catalog service might provide an API endpoint to get product details, product ID. The contract states that if you send it a product ID, it will return product name, description, price, etc. in a specific format. The service might internally get this data from a NoSQL database, a cache, or even another internal service. The calling service doesn't need to know or care about these internal workings. This strict adherence to API contracts provides immense benefits. Loose coupling. As long as a service adheres to its defined API contract, its internal implementation can change drastically without affecting its consumers. The product catalog service could switch its database from SQL to NoSQL, and as long as get product details, product ID, still returns the same data in the same format, other services remain unaffected. Scalability. APIs allow services to communicate over a network, enabling them to be deployed independently and scaled horizontally. Technology agnosticism. Services using different programming languages or technologies can still communicate effectively as long as they respect the API contract. In essence, data hiding and API contracts together define the explicit boundaries and interaction mechanisms crucial for microservices to truly function as independent, interchangeable components. With these core concepts under our belt, we are now ready to explore how to effectively design these individual services and orchestrate their interactions, which will be the focus of our next chapter. Chapter 3. Designing your microservices, principles and patterns. You've grasped the fundamental ideas behind microservices. Their small, autonomous, and independently deployable nature, their relationship with bounded contexts, and the importance of the single responsibility principle and clear API contracts. Now comes the exciting, yet challenging part. How do you actually design microservices from scratch? Or, more commonly, how do you break down an existing monolithic application into these smaller, distributed units? Designing microservices isn't a one-size-fits-all formula. It's an art form that blends business understanding with technical acumen. This chapter explores various strategies and principles to help you draw effective boundaries between services, ensure they remain loosely coupled, and avoid common pitfalls that can undermine the very benefits microservices promise. 3.1 Decomposition Strategies. By business capability, subdomain, or workflow. One of the first and most critical decisions in microservice design is how to delineate service boundaries. Where do you cut the application into independent pieces? Several decomposition strategies exist, each with its strengths and weaknesses. By business capability, recommended. This is generally considered the most robust and natural way to decompose an application. A microservice defined by business capability encapsulates a specific, well-defined business function. These capabilities are often long-lived and relatively stable aspects of an organization, independent of changes in user interfaces or operational flows. How it works: identify core business functions such as order management, customer relationship management, product catalog, payment processing, or shipment tracking. Each of these becomes a candidate for a dedicated microservice. Example: Speedy Ship. Instead of a monolithic logistics system, you might have customer service manages customer profiles. Order service handles creating and tracking orders. Payment service processes financial transactions. Shipping service manages package pickup, delivery, and routing. Notification service sends email, SMS updates for various events. Advantages: stable boundaries. Business capabilities tend to be more enduring than specific user stories or workflows. Team alignment. Services align well with cross-functional teams, allowing them to own a complete business function. True autonomy. Each service can evolve independently without intimate knowledge of other parts of the business. Considerations requires a deep understanding of the business domain. By subdomain, building on domain-driven design. Drawing directly from domain-driven design, DDD, decomposition by subdomain is highly effective, especially for complex domains. A business domain can be divided into subdomains, each representing a distinct area of expertise or concern. These subdomains can be classified, core domains, the unique, differentiating aspects of your business that provide a competitive advantage, e.g., Speedy Ship's proprietary route optimization for logistics. Supporting domains, necessary but not differentiating functions that support the core business, e.g., customer support, reporting. Generic domains, off-the-shelf solutions that are common across many businesses and don't provide competitive advantage, e.g., authentication, logging. How it works. Once subdomains are identified, services are created to encapsulate the logic and data for each. Core domains often justify more investment in custom microservices, while generic domains might use third-party services. Advantages: provides a systematic way to manage complexity, prioritizing where to put development effort. Directly maps to the concept of bounded contexts. Considerations: requires familiarity with DDD concepts. By workflow or use case, generally discouraged. This strategy involves creating services based on specific user journeys or transactional flows. For example, an order placement service might handle the entire end-to-end process of placing an order, from validating customer details to updating inventory and processing payment. How it works: identify common user workflows, e.g., customer places an order, user registers, admin generates report. Each workflow could become a service. Disadvantages: high coupling. Services often become tightly coupled to specific workflows, leading to cascading changes. If the order placement workflow changes, it might impact multiple services. Shared data logic. A single business capability, like customer, might be duplicated across multiple workflow-based services, leading to inconsistencies and maintenance nightmares. Orchestration challenges. These services typically require heavy orchestration, making them harder to reason about and scale independently. When to use: rarely. In very narrow scenarios where a self-contained, linear process genuinely has no shared components with other business capabilities. Even then, it's often better visualized as coordination between capability-driven services rather than a service itself. Practical application. A design exercise. To determine effective boundaries, gather business stakeholders and domain experts. Ask questions like, what are the core functions of our business? What are the distinct areas where different teams operate? If we wanted to change how payments are handled, what parts of the system would need to change? Answering these questions can help you identify strong candidates for business capability-based services. 3.2 Domain-Driven Design, DDD Basics for Microservices. We've already touched upon bounded contexts from domain-driven design, DDD, as a key concept for service decomposition. But DDD offers more than just context boundaries. It provides a powerful mindset and toolset for building complex software systems, particularly valuable in a microservice landscape. At its core, DDD emphasizes focus on the business domain. Your software model should deeply reflect the realities and complexities of the business it serves. Collaboration with domain experts. Close communication and collaboration between software developers and business experts are crucial to ensure the software accurately captures the domain logic. Here are a few more DDD concepts highly relevant to microservices. Ubiquitous language. This is a shared, common vocabulary established between domain experts and developers. Every term, concept, and process within a bounded context should have a precise, unambiguous meaning. This language is then used consistently in code, documentation, and discussions. For example, if Speedy Ship defines a consignment as a unique shipment of goods, then every developer, product manager, and logistics expert uses this term consistently to mean the same thing. This reduces miscommunication, especially when services communicate across boundaries. Aggregates. Within a bounded context, An aggregate is a cluster of associated domain objects that are treated as a single unit for data changes. It has a single aggregate root, which is the only object external entities can hold references to. All operations that modify the objects within the aggregate must go through the aggregate root. Example: in an order-bounded context, an order itself might be the aggregate root containing order items. You wouldn't directly modify an order item outside the context of its order. Importance for microservices. Aggregates define consistency boundaries. This means that a microservice often exposes operations that operate on an entire aggregate. This helps maintain data consistency within a service and avoids distributed transactions where possible. Repositories. Repositories are objects that encapsulate the logic required to retrieve and store aggregates. They don't typically expose direct database access, but provide methods like find by orderid or save order. Importance for microservices. Repositories abstract away the data storage mechanism. A microservice is the sole responsible party for its aggregate's persistence, which reinforces the database per service concept. We'll cover this in depth in Chapter 5. By applying DDD principles, you aren't just breaking down a system into smaller pieces. You're breaking it down in a way that makes business sense, leading to services that are logically cohesive and aligned with organizational structures. 3.3. Loose coupling and high cohesion. These two principles are the bedrock of good microservice design, directly enabling the benefits we discussed in Chapter 1. Loose coupling. Loose coupling means that services are designed to be as independent as possible, with minimal dependencies on each other's internal implementation details. A change in one service should have little to no impact on other services. How to achieve it? Strict API contracts. Services should only interact through well-defined APIs. As long as the API contract, input-output errors, remain stable, the internal implementation can freely change. Avoid shared databases. This is a cardinal rule. Direct database sharing creates a massive coupling dependency. If Service A queries Service B's database, then Service A breaks if Service B changes its schema. Asynchronous communication. Favor event-driven communication. See Chapter 4 where possible, as it naturally leads to looser coupling than synchronous request-response interactions. Independent deployments. The ability to deploy one service without affecting others is a strong indicator of loose coupling. Why it's important. Loose coupling enables independent development, deployment, and scaling. It allows teams to work faster and reduces the risk of introducing unintended side effects across the system. It fosters resilience because a failure in one loosely coupled service is less likely to cascade and bring down the entire system. High cohesion. High cohesion means that the elements within a single service are logically related and work together towards a single, well-defined purpose. If a service processes payments, all its internal components, classes, functions, data structures, should be related to payment processing. How to achieve it? Adhere to SRP. A service with a single responsibility naturally achieves high cohesion. Align with bounded contexts. Services that correspond to a single bounded context are inherently cohesive. Minimize cross-cutting concerns. Try to encapsulate common functionality, like logging or authentication, in separate dedicated services or infrastructure components, rather than scattering it throughout many services, unless it's specific to that service's capability. Why it's important. High cohesion makes a service easier to understand, test, and maintain. When a service is cohesive, any changes needed for its functionality are generally localized within the service itself, reducing the impact on other parts of the system. It contributes to making services truly small and manageable. The interplay between loose coupling and high cohesion is vital. You want your services to be highly cohesive internally, doing one thing well, and loosely coupled externally, not dependent on each other's internal details. This balance is the hallmark of a well-designed microservice architecture. 3.4. Avoiding distributed monoliths. Common pitfalls in design. The journey to microservices is fraught with potential missteps. One of the most common and damaging failures is the creation of a distributed monolith. An application that has been broken into multiple services, but still exhibits the rigid coupling, slow deployments, and lack of resilience characteristic of a traditional monolith. It's like breaking your all-in-one kitchen appliance into separate pieces, but then gluing them back together. Here are some common pitfalls that lead to distributed monoliths and how to avoid them. Shared database across services. The problem: the single largest contributor to a distributed monolith. If multiple services directly access the same database tables, changing the schema for one service inevitably impacts others. This forces coordinated deployments, negating the independent deployability benefit. The fix: database per service. Each microservice should own its data store and be the sole authority for that data. If another service needs data from it, it must request it via the owning service's API. We will deep dive into this in Chapter 5. Too granular or too coarse-grained services. The problem: too granular nanoservices. Breaking services down into ridiculously tiny pieces, e.g., a service just for validate email. This leads to excessive network calls, operational overhead, complex deployments, and a death by 1,000 cuts, where managing hundreds or thousands of tiny services becomes unmanageable. Too coarse-grained mini-monoliths. Services that encapsulate too much functionality, violating SRP and bounded contexts. These services become bottlenecks and are hard to scale or evolve independently. The fix: start with services that align with key business capabilities, as discussed in 3.1. Aim for services that are small enough to manage, but large enough to matter. It's often better to start slightly larger and refactor into smaller services as understanding evolves. The strangler fig pattern we'll discuss later. Synchronous communication everywhere. The problem: relying exclusively on synchronous request-response communication, one service calls another and waits for a response. While sometimes necessary, overuse creates tight runtime coupling. If one service is down or slow, it can cascade and impact many other services, just like a chain reaction. The fix: embrace asynchronous communication patterns, e.g., message queues, event streams, where services communicate by sending and receiving messages without waiting for an immediate response. This drastically reduces coupling and improves resilience. We'll explore this in detail in Chapter 4. Excessive cross-service transactions/distributed transactions. The problem: trying to maintain strong transactional consistency, ACID properties like all or nothing, across multiple services. This is incredibly complex to implement correctly in a distributed system and often leads to tight coupling and poor performance. The fix: embrace eventual consistency and design with sagas, a sequence of local transactions. This acknowledges that data across distributed services might not be perfectly synchronized at every millisecond, but will converge over time. This is a fundamental shift in thinking about data consistency. We'll cover this in Chapter 5. Organizational and cultural misalignment, Conway's Law. The problem: trying to implement microservices within a traditional, functionally siloed organization, e.g., separate database, backend, and front-end teams. Microservices thrive with cross-functional teams that own services end-to-end. If teams are organized differently, the architecture will often reflect the organizational structure, leading to a distributed monolith. The fix: align your teams with your services. Conway's Law states that organizations which design systems are constrained to produce designs which are copies of the communication structures of these organizations. This means if you want a microservice architecture, you need loosely coupled, highly cohesive teams. Designing microservices effectively requires a deep understanding of business domains, a disciplined adherence to principles like SRP, loose coupling, and high cohesion, and a constant vigilance against common pitfalls. By carefully considering these strategies and avoiding the common traps, you can lay the groundwork for a truly agile, resilient, and scalable software system. Our next step is to understand how these independent services talk to each other, the language of microservices. Chapter 4: Communication between services, the language of microservices. We've established that microservices are autonomous, independently deployable units, each owning its own data and responsibility. but applications rarely consist of a single isolated service. To deliver valuable business functionality, these services must interact with each other, exchanging information and coordinating actions. This inter-service communication is the language of a microservices architecture. Choosing the right communication style and patterns is critical. The wrong choice can negate the benefits of microservices by introducing tight coupling, performance bottlenecks, and increased operational complexity. This chapter will explore the two primary communication paradigms, synchronous and asynchronous, discuss their implications, and help you understand when to use each. 4.1 Synchronous Communication. REST-TFL APIs and RPC. Synchronous communication is perhaps the most familiar interaction model. When one service, the client, makes a synchronous call to another service, the server, the client sends a request and then waits for a response before continuing its processing. It's like a phone call. You dial, you wait for the other person to answer, you speak, and you wait for their reply. The most common technologies for synchronous communication in microservices are REST-TFL APIs, representational state transfer. REST is an architectural style for distributed hypermedia systems. It's widely adopted for web services due to its simplicity, statelessness, and reliance on standard HTTP methods: GET, POST, PUT, DELETE. How it works. A client service sends an HTTP request, e.g., GET orders 123 to retrieve order details, or POST products to create a new product, to a specific Uniform Resource Identifier, URI, exposed by the server service. The server processes the request and sends back an HTTP response, typically containing data in a standard format like JSON or XML, along with an HTTP status code, e.g., 200 OK, 404 not found, 500 internal server error. Example, speedy ship. The customer UI service needs to display a customer's order history. It makes a get/customers/customer ID/orders request to the order service. The order service receives the request, queries its database for the relevant orders, and returns them as a JSON array. Pros: simplicity and familiarity. HTTP and REST are widely understood, and many tools and libraries support them. Statelessness. Each request from client to server contains all the information needed to understand the request. The server doesn't store any client context between requests, which simplifies scaling. Readability. URLs and HTTP methods make the purpose of requests often self-describing. Tooling. Extensive tooling for testing, debugging, and documenting REST APIs. Cons. Tight runtime coupling. The client service is blocked, waiting for the server's response. If the server service is slow, unavailable, or experiences an error, the client service will be directly impacted or even fail. Increased latency. Each hop over the network adds latency. For operations requiring multiple synchronous calls across several services, cumulative latency can become significant. Cascading failures. A failure in one service can quickly propagate through a chain of synchronous calls, leading to widespread outages. We'll discuss resilience patterns to mitigate this in Chapter 6. RPC, Remote Procedure Call. RPC systems allow a program to call a procedure or function in a different address space, typically on a remote server, as if it were a local procedure call. While less common than REST for public-facing APIs, RPC frameworks like gRPC and Apache Thrift are popular for inter-service communication within a microservices architecture. How it works. RPC frameworks typically define a service contract using an interface definition language, IDL, specifying the methods, parameters, and return types. Specialized tools then generate client stubs and server skeletons in various programming languages, allowing developers to call remote methods just like local ones. Example, speedy ship. The payment service might use gRPC to call a method like process payment, payment details on a fraud detection service. Pros: strong typing and performance. IDLs enforce strict type checking, catching errors at compile time. They often use binary serialization formats, which can be more compact and faster than JSON XML, leading to lower latency and higher throughput. Multiplexing and streaming. gRPC, for instance, supports advanced communication patterns like bidirectional streaming over a single TCP connection, which can be more efficient for certain use cases. Cons: less human-readable. Binary protocols and generated code are less intuitive to read and debug than plain HTTP JSON. Steeper learning curve. Requires understanding a specific framework and IDL. Still synchronous by nature. Despite performance benefits, the fundamental blocking nature of typical RPC calls remains, leading to similar coupling and cascading failure risks as REST. When to use synchronous communication. Synchronous communication is generally preferred for requests where the client requires an immediate response to continue its execution, e.g., UI displaying data to a user. The operation is simple, doesn't involve long-running processes, and doesn't require complex coordination across many services. The services are tightly coupled by design for a specific transactional boundary, which should be minimized in microservices. However, excessive synchronous communication is a major anti-pattern in microservices. It often leads to a distributed monolith, where the system is fragmented but still behaves like a single, fragile unit due to tight runtime dependencies. 4.2 Asynchronous communication. Message queues and event-driven architecture. In contrast to synchronous communication, asynchronous communication allows a client service to send a request or message and continue its processing without immediately waiting for a response. The response, if any, will arrive at a later time, or the sender may not even expect one. It's like sending a letter or an email. You send it, and then you can move on to other tasks. You don't wait at the mailbox for a reply. Asynchronous communication is invaluable in microservices for enabling true loose coupling and resilience. The primary mechanisms for asynchronous communication are message queues and event-driven architectures. Message queues, message brokers. A message queue acts as an intermediary, a message broker, between sender services, producers, and receiver services, consumers. Producers send messages to a queue, and consumers retrieve messages from the queue for processing. How it works: a producer service creates a message, e.g., order placed. It sends this message to a message broker, e.g., RabbitMQ, Apache Kafka, Amazon SQS. The message broker durably stores the message in a queue. A consumer service subscribes to that queue or a specific topic event type. The consumer retrieves the message, processes it, and then acknowledges its completion to the broker. Example: speedy ship. When the order service successfully processes a new order, it puts an order placed message onto a queue. The notification service consumes this message to send a confirmation email to the customer. The inventory service also consumes the order placed message to decrement stock levels. The billing service consumes the message to initiate payment processing. Pros: decoupling. Producer and consumer services don't need to know about each other's direct availability. The broker acts as an intermediary, significantly reducing runtime dependencies. Resilience. If a consumer service is temporarily down, messages remain in the queue until it becomes available again. The producer continues to operate normally. Scalability. You can add more consumer instances to process messages from a queue in parallel, scaling throughput without impacting the producers. Load leveling. Message queues can absorb spikes in traffic, smoothing out the load on consumer services. Fan-out pub-sub. Many message brokers support a publish-subscribe pub-sub model, where a single message published by one service can be consumed by multiple subscribing services. This enables powerful event-driven architectures. Cons: increased complexity, introduces a new component, the message broker, to manage and monitor. Debugging challenges. Tracing the flow of a single business transaction across multiple asynchronous messages and services can be complex. Eventual consistency often leads to eventual consistency, meaning data might not be immediately consistent across services, which requires careful design. More on this in Chapter 5. Ordering guarantees. Ensuring message order can be tricky, especially with multiple consumers. Event-driven architecture. Event-driven architecture, EDA, is an architectural pattern that relies on the production, detection, consumption, and reaction to events. An event represents a significant change of state within a system, e.g., order placed, payment approved, product shipped. Services communicate by publishing events that other services can subscribe to and react to. Message queues are a common implementation choice for the message broker component in an EDA. How it works. Services emit events, facts about what happened, to an event bus or message broker. Other services interested in those events subscribe to them and react accordingly. The publisher of an event typically knows nothing about its subscribers. Example, speedy ship. Order service emits an order-created event. Inventory service listens for order created and reserves inventory. Once reserved, it emits an inventory reserved event. Payment service listens for inventory reserved and attempts payment. On success, it emits a payment approved event. Notification service listens for order created, payment approved, and product shipped events to send various customer communications. Pros: extreme decoupling. Services are highly independent. A publisher doesn't even know if there are any subscribers. Scalability. Events can be processed by many consumers in parallel. Flexibility and extensibility. Easy to add new services that react to existing events without modifying existing services. This makes it much easier to extend system functionality. Auditability. Event streams can provide a durable audit log of state changes in the system. Cons: debugging and monitoring. Tracing the flow of complex business processes across multiple event hops can be challenging. Data consistency. Reliance on eventual consistency requires careful design. Error handling. What happens if a consumer fails to process an event? Retries and dead letter queues are essential. Complexity. Introduces new architectural patterns and infrastructure components, brokers, event storage, that need to be managed. 4.3. Choosing the right communication style. The choice between synchronous and asynchronous communication is not an either-or decision. Most mature microservice architectures employ a mix of both. The key is to make informed decisions based on the specific interaction's requirements. Use synchronous communication when real-time response required. The user interface or calling service absolutely needs an immediate response to proceed, e.g., login authentication, retrieving a single user profile to display. Simple request response. The interaction is a straightforward query or command where the caller awaits a direct result. Transactionality. Within a single service boundary. When an operation needs to complete entirely or roll back within the scope of a single service. Use asynchronous communication when decoupling is paramount. You want services to evolve and deploy independently without direct runtime dependencies. Long-running processes. An operation might take a significant amount of time, and the caller doesn't need to wait, e.g., video encoding, batch processing, complex report generation. Scalability and resilience are key. You need to handle high throughput, absorb traffic spikes, and ensure the system remains available even if some services are temporarily unavailable. Fan out many consumers. Multiple services need to react to the same event. Cross-service workflows that can tolerate eventual consistency. For business processes that span multiple services and don't require immediate transactional consistency across all steps. The rule of thumb. Prefer asynchronous communication where possible to achieve maximum loose coupling and resilience. This should be your default consideration. Use synchronous communication for queries and user interface-driven interactions where an immediate response is crucial. 4.4 Idempotency and handling failures in communication. Regardless of the communication style, distributed systems inevitably encounter network issues, service failures, and retries. This highlights two crucial concepts. Idempotency. An operation is idempotent if it can be applied multiple times without changing the result beyond the initial application. In other words, calling an idempotent operation once has the same effect as calling it 50 times. Why it matters. In distributed systems, retries are common. If a message is sent but fails to receive an acknowledgement, the sender might reattempt the operation. If the operation isn't idempotent, this retry could lead to duplicate processing, e.g., charging a customer twice, creating two identical orders. Example, non-idempotent. Post orders, creating a new order. Sending this twice would create two orders. Idempotent, PUT orders 123, updating order 123. Updating with the same data multiple times has no additional effect after the first successful update. For post-operations, a common approach is to include a unique idempotency key, like a UUID, in the request. If the server receives the same idempotency key twice, it processes the request only once or returns the result of the first processing. Application. All operations exposed by your microservices, especially those that modify state, should be designed to be idempotent or have mechanisms to handle potential retries gracefully. Handling failures in communication. Failures are a certainty in distributed systems. Services crash, networks become unreliable, and messages get lost. Effective communication strategies must account for this. Timeouts and retries. Clients should implement reasonable timeouts when making synchronous calls. If a service doesn't respond within the timeout, the client can retry the request. However, blind retries can overload a struggling service. Circuit breakers. A pattern that prevents an application from repeatedly trying to perform an operation that is likely to fail. If a service consistently returns errors, e.g., 5xx, the circuit breaker trips, short-circuiting subsequent requests directly to a fallback mechanism or an error state, giving the failing service time to recover. More on this in Chapter 6. Dead letter queues, DLQs. In asynchronous systems, if a message repeatedly fails to be processed by a consumer, e.g., due to invalid data or a bug in the consumer, it can be moved to a dead letter queue. This prevents the message from blocking the main queue and allows operators to inspect and potentially reprocess the problematic messages manually or with a dedicated error handling service. Observability. Without knowing what's happening, it's impossible to diagnose communication failures. Robust logging, monitoring, and distributed tracing are essential to identify bottlenecks or failures in inter-service communication. See Chapter 7. Choosing and implementing communication styles is a foundational aspect of microservice design. While challenging, mastering these patterns allows you to build highly decoupled, resilient, and scalable systems that can truly deliver on the promise of microservices. Next, we will tackle one of the most complex aspects: how to manage data in a world where every service owns its own data. Chapter 5. Data management in a decentralized world. In a monolithic application, managing data is relatively straightforward. Typically, a single, large database sits underneath the entire application, and all components interact with it. This centralized data model simplifies transactions and ensures immediate consistency. However, as we venture into the decentralized world of microservices, this monolithic database becomes a significant anti-pattern. Sharing a single database tightly couples services, undermining their autonomy and independent deployability. Therefore, one of the most fundamental and challenging shifts in microservice architecture is decentralizing data management. This chapter will explore the concept of database per service, delve into the complexities of achieving data consistency across services, and offer strategies for managing shared data and migrations. 5.1 Database per service. Why and how? The principle of database per service is a direct consequence of the microservice characteristic of autonomy. Each microservice should own its domain data exclusively. This means a service's data store is private to that service. No other service should directly access another service's database. If another service needs data owned by another service, it must retrieve it via the owning service's exposed API. Why database per service is critical. Enables independent deployability. If two services share a database, a schema change in one service's table might break the other. This forces coordinated deployments, eliminating one of microservices' key benefits. With separate databases, teams can evolve their data schemas independently. Facilitates technology diversity. Not all data is best stored in the same type of database. A product catalog service might benefit from a NoSQL document database for flexible schemaless product definitions, while a payment service requires the transactional integrity of a relational database. Recommendation service might use a graph database. Database per service allows each service to choose the database technology best suited for its specific data needs and workload. Encapsulates business logic. Since the service explicitly owns its data, all business logic related to that data is encapsulated within the service. This reinforces the single responsibility principle and helps maintain clear boundaries. Improves resilience. If one service's database encounters issues, it ideally only affects that service, rather than bringing down the entire application as a shared database failure might. Simplified scaling. Each service can scale its database independently based on its specific load requirements, rather than having to scale a single, giant database for the entire application. How to implement database per service. Logical versus physical separation. Database per service implies logical separation. While you could have physically separate database instances for each service, e.g., separate containers, separate cloud database instances. It's also common for multiple services to share a single database server instance, but use separate, logically isolated schemas or databases within it. The key is that the application code of one service never directly accesses the table's collections of another service. Encapsulation. The service defines an API, e.g., REST-TFL endpoints or message-based interfaces that consumers use to interact with its data. The internal data model and storage mechanism are hidden. Data duplication, when appropriate. Occasionally, a service might need a copy of some data owned by another service for performance or query optimization. For example, the shipping service at SpeedyShip might need a copy of the customer's shipping address for quick lookup during delivery route optimization, even though the customer service owns the authoritative customer data. This duplication must be handled carefully, typically by subscribing to events emitted by the owning service when its data changes, see below. 5.2 Managing data consistency across services. Sagas and eventual consistency. One of the significant challenges with database per service is how to manage business transactions that span multiple services. In a monolith, a multi-step operation could be wrapped in a single ACID, atomicity, consistency, isolation, durability transaction. If any step failed, the entire transaction would roll back. In a microservices architecture, you cannot have single ACID transactions that span multiple services and their respective databases. Such attempts would introduce tight coupling and significant performance bottlenecks. Instead, microservices embrace eventual consistency and patterns like sagas. Eventual consistency. Eventual consistency means that data across a distributed system might not be perfectly synchronized at all times, but it eventually converges towards a consistent state. Analogy: think of propagating changes in a large community. If you tell one person a piece of news, it takes time for that news to spread throughout the entire community. Eventually, everyone gets the news, but there's a period where some people know and others don't. Implication for microservices. When a business operation spans multiple services, the data reflecting that operation might not become consistent globally instantaneously. For example, when an order is placed at SpeedyShip, the order service creates the order. It sends an event to the inventory service to deduct stock. It sends another event to the payment service to process payment. These events are processed asynchronously. There's a brief window of time where the order exists in the order service, but the inventory might not yet be deducted, and payment might not yet be confirmed. Acceptance. Developers and business stakeholders must understand and design for eventual consistency. It requires a shift in mindset from immediate transactional integrity everywhere. Sagas. Coordinating distributed transactions. A saga is a sequence of local transactions, where each local transaction updates the state of a single service and publishes an event that triggers the next local transaction in the saga. If a local transaction fails, the saga executes a series of compensating transactions to undo the changes made by the preceding transactions. There are two main ways to coordinate sagas. Choreography-based saga, event-driven. How it works. Each service participating in the saga publishes events upon completing its local transaction. Other services interested in those events subscribe to them and react by executing their own local transaction, potentially publishing new events. Example, speedy ship order placement. Order service creates an order local transaction, publishes order created event. Inventory service consumes order created, reserves inventory local transaction, publishes inventory reserved event. Payment service consumes inventory reserved, processes payment local transaction, publishes payment processed event. Shipping service consumes payment processed, initiates shipping local transaction, publishes shipping initiated event. Failure scenario. If payment service fails to process payment, it publishes a payment failed event. Inventory service consumes this, releases inventory, compensating transaction, publishes inventory released. Order service consumes payment failed, marks order as failed, compensating transaction. Pros, highly decentralized, promoting loose coupling. Services are independent. Cons, can be difficult to monitor and debug due to the lack of a central coordinator. The global state of the saga is defined implicitly by the state of individual services. Orchestration-based saga, how it works. A dedicated service, the saga orchestrator, manages the entire workflow. It sends commands to participant services, telling them what to do. Each participant executes its local transaction and sends a response back to the orchestrator confirming success or failure. The orchestrator then decides the next step or initiates compensating transactions if a failure occurs. Example, speedy ship order placement. Order orchestrator receives and place order command. It sends a create order command to order service. On success, it sends a reserve inventory command to inventory service. On success, it sends a process payment command to payment service. Failure scenario. If payment service responds with payment failed, the order orchestrator sends a release inventory command to inventory service and a cancel order command to order service. Pros. Centralized logic for the saga, easier to monitor and manage the overall flow. Simpler rollback logic. Cons, the orchestrator can become a single point of failure or a bottleneck if not designed carefully. Less decentralized than choreography. When to use which saga type? Choreography. Best for simple sagas, 2 to 3 steps, when all participants are known and there's less need for complex error handling logic. Orchestration. Better for complex sagas with many participants, significant business logic, and when it's critical to guarantee completion or full rollback. 5.3 When to share data and when not to. The database per service principle is fundamental, but sometimes a limited form of controlled data sharing or replication can be considered, though always with caution. When not to share data, the default stance. Do not share the database itself. Never allow one service to directly query or write to another service's database. This is the primary rule that, if broken, leads to a distributed monolith. Do not share tables collections. While an organization might host multiple conceptual databases on the same physical server, the logical separation and ownership of data per service must be maintained. Each service works with its own dedicated tables collections. When to carefully share data or derive data. Sometimes, for performance reasons or to enable complex queries that span multiple contexts. A service might need access to a subset of another service's data. This should be achieved via eventual consistency through replication or derived data, not direct database access. Denormalization/data duplication. How it works. A service, e.g., shipping service, might need basic customer information, name, address, that is owned by the customer service. Instead of making a synchronous call to customer service for every shipping request, the shipping service could maintain its own denormalized copy of the necessary customer data. Mechanism: the customer service would publish events, e.g., customer address updated when customer data changes. The shipping service would subscribe to these events and update its local copy. Considerations: this introduces eventual consistency for the duplicated data. Requires careful planning for data synchronization and handling stale data. Only replicate the bare minimum necessary data. Shared read-only views, materialized views. How it works. For complex analytical queries or general reporting that needs to combine data from multiple services, you might create a separate read-only reporting database or materialized views. This is often built by subscribing to events from multiple services, transforming them, and loading them into a data warehouse or data lake optimized for analytics. Mechanism: services publish events about their data changes. A separate reporting service, or ETL, extract, transform, load process consumes these events and populates the reporting database. Considerations: this data is typically eventually consistent and not suitable for real-time operational queries. Its purpose is for analytics and insights, not for the core transactional flow of the application. These approaches are exceptions to the database per service rule, used only when strictly necessary, and they always carry the caveat of needing to manage eventual consistency. 5.4 Data migrations and versioning in microservices. Data migration and versioning in microservices become more complex due to the independent nature of services and their databases. Data migrations, schema evolution, backward compatibility. When changing a service's database schema, always strive for backward compatibility. This means the new version of the service, v2, can still read and write data that was created by the old version, v1, and ideally, new v1 code can also make sense of data written by v2, though this is harder. Evolutionary database design. Instead of big bang schema changes, prefer small, incremental, additive changes. Never delete columns or tables without a lengthy deprecation period. Phased rollout. v1 old and v2 new run simultaneously. Deploy the new version, v2, of the service that can read both old and new data formats and write in the new format or both. Data migration. If necessary, background processes migrate all existing data from the old format to the new format. Deprecate old format. Once all data is migrated and services are confirmed to be operating on the new format, remove the old data format support from the service and database. Automated migrations. Use database migration tools, e.g., Flyway, Liquibase for relational databases, specific tooling for NoSQL databases to manage schema changes automatically and consistently. Data versioning, API versioning. While database schemas evolve internally to a service, the external API that exposes data to other services also needs careful versioning. Why version APIs? When you change the structure of data returned by an API or the parameters it expects, you might break consuming services. Strategies for API versioning. URL versioning. Include the version number in the URL, e.g., /API/v1/customers/API/v2/customers. Easy to understand, but can lead to URL proliferation. Header versioning. Include the version in an HTTP header, e.g., except applications/vndmyipv1 plus JSON, cleaner URLs but less discoverable. No versioning, backward-forward compatibility. Strive for compatibility as much as possible. Only add new fields, never remove or rename existing ones. Deprecate fields but keep them for a long time. This is the ideal but most challenging approach. Deprecation and communication. When a new API version is introduced, clearly communicate the deprecation of older versions. Provide a transition period and, ideally, tools or guides to help consumers migrate. Managing data in a microservices architecture is arguably the most complex aspect of the transition from monoliths. It requires a fundamental shift in thinking from centralized, transactional consistency to decentralized, eventually consistent models. While challenging, mastering these patterns is essential for unlocking the true benefits of agility and scalability that microservices promise. With data taken care of, our next focus will be on the vital infrastructure and support systems that enable microservices to run effectively. Chapter 6: Building Blocks for Microservices Infrastructure and Support. So far, we've focused on the conceptual design of microservices, what they are, how to decompose them, and how they communicate and manage data. But these independent units of software don't just magically appear and run themselves. They require a robust foundation, a comprehensive infrastructure, and a set of supporting tools and patterns to operate effectively, scale, and remain resilient in the face of failure. This chapter delves into the essential building blocks that underpin a successful microservices deployment. We'll explore how services find each other, how external consumers access them, and critical patterns for maintaining stability and performance in a distributed environment. We'll also touch upon the transformative technologies that have become synonymous with modern microservices deployments: containerization and orchestration. 6.1 Service Discovery. Finding your services. In a monolithic application, components communicate directly because they are all part of the same process. In a microservices architecture, services often run on different machines or in different containers, and their network locations, IP addresses and ports, are dynamic. Services can be deployed, scaled up, scaled down, or crash and restart on new locations. How then does one service find and communicate with another? This challenge is solved by service discovery. The problem: imagine order service needs to call inventory service. Inventory service instances might constantly change their locations, especially in a dynamic cloud environment where instances scale up and down. Hardcoding IP addresses or maintaining a static list is impractical and fragile. The solution: service discovery mechanisms. There are two primary patterns for service discovery: client-side service discovery. How it works: services register themselves with a service registry upon startup. When a client service wants to call another service, it queries the service registry to get a list of available instances of the target service. The client then uses a load balancing algorithm, like round robin, to choose one instance and sends the request directly. Components. Service provider. The service that exposes an API, e.g., inventory service. It registers its network location with the service registry. Service registry. A database or server that contains the network locations of all available service instances, e.g., Netflix Eureka, HashiCorp Console, Apache Zookeeper, Kubernetes API server. Service consumer. The service that wants to call another service, e.g., order service. It queries the service registry. Pros: fewer network hops as the client connects directly to the target service. The client has intelligent load balancing capabilities. Cons: the client service must implement discovery logic, potentially requiring a discovery client library in each programming language. Server-side service discovery. How it works: the client service makes a request to a router or load balancer, which is aware of the service registry. This router load balancer then queries the service registry, gets the network location of an available instance of the target service, and forwards the request to it. The client service doesn't need to know anything about discovery. Components. Same as client-side, but with an intermediary router load balancer, e.g., AWS Elastic Load Balancer, ELB, Nginx, Kubernetes kube-proxy/service mesh like Istio. Pros: simpler for the client service, it just calls the router. Discovery logic is centralized in the router. Cons: adds an extra network hop and a potential bottleneck if the router is not robust or scales well. Health checks. For service discovery to be effective, the service registry needs to know which service instances are healthy and available. Services typically regularly send heartbeats or health checks to the service registry. If a service instance stops responding, it's deregistered and taken out of rotation. Service discovery is fundamental for making microservices dynamically scalable and resilient in cloud environments. 6.2 API Gateways. The entry point to your architecture. While individual microservices expose their own APIs, a direct external client, like a web browser or mobile app, typically doesn't want to make dozens of calls to various backend services to render a single user interface. This is where an API gateway comes in. An API gateway is a single, unified entry point for all external clients into the microservices ecosystem. It acts as a reverse proxy, routing requests to the appropriate backend services. Key functions of an API gateway: request routing. It directs incoming requests to the correct internal microservice based on the URL path, HTTP method, or other criteria. E.g., /API/products goes to product service, /API/orders goes to order service. API composition aggregation. It can aggregate responses from multiple internal services into a single response for the client. For example, a mobile app might request a dashboard view, and the API gateway fetches data from user profile service, order history service, and notification service and combines it. Authentication and authorization. It can handle security concerns like verifying API keys, authenticating users, and applying authorization policies before routing requests to backend services. This offloads complexity from individual microservices. Rate limiting controls the number of requests a client can make within a certain timeframe to prevent abuse or overload. Logging and monitoring provides a central point for collecting metrics and logs related to API usage. Protocol translation can translate between different communication protocols, e.g., client uses REST, but backend microservice uses gRPC. Load balancing, often in conjunction with service discovery, distributes incoming traffic across multiple instances of backend services. Example, Speedy Ship. A customer using the Speedy Ship mobile app would make one call to the API gateway. The gateway authenticates the user, then intelligently routes or aggregates results from the customer service, order service, and shipping service to display the customer's dashboard. Pros: simplified clients. External clients only need to know one URL endpoint. Reduced network traffic aggregates multiple internal calls into one external call. Centralized concerns offloads common cross-cutting concerns, security, monitoring, etc. from individual microservices. Hides microservice topology. Clients are shielded from the internal complexity of the microservices architecture. Cons: single point of failure bottleneck. If not properly designed, scaled, and managed, the API gateway can become a bottleneck or a single point of failure. Redundancy and high availability are crucial. Increased complexity introduces another component to develop, deploy, and manage. Potential for monolithic gateway. If too much business logic or heavy orchestration is implemented in the gateway, it can become a monolithic gateway that's hard to change. Popular API gateway technologies include Nginx, Kong, Amazon API Gateway, Google Apigee, and Spring Cloud Gateway. 6.3 Load balancing and resilience patterns, circuit breakers, bulkheads. In a distributed microservices environment, failures are not exceptions. They are inevitable. Network issues, hardware failures, software bugs, or sudden traffic spikes can all cause services to become unavailable or unresponsive. Robust microservices architectures incorporate resilience patterns to handle these failures gracefully. Load balancing. Beyond what might be handled by an API gateway or service discovery, load balancing is crucial for distributing incoming network traffic across multiple servers or service instances. Its goal is to maximize throughput, minimize response time, and prevent any single server from becoming overloaded. How it works. A load balancer sits in front of a group of servers and distributes client requests among them using various algorithms, e.g., round-robin, least connections, IP hash. Benefits: improves application responsiveness, increases availability, and allows for horizontal scaling. Resilience patterns. These patterns help services gracefully degrade or recover from failures without cascading into a system-wide outage. Circuit breaker pattern concept prevents an application from repeatedly trying to perform an operation that is likely to fail. It's like an electrical circuit breaker that trips to prevent damage when there's an overload. How it works. A proxy or client wrapper monitors calls to a service. If the error rate or latency exceeds a certain threshold, the circuit breaker trips, and for all subsequent calls, it immediately returns an error or a fallback response without even attempting to call the failing service. After a configurable sleep window, it enters a half-open state, allowing a few test requests to pass through. If they succeed, it closes the circuit. Otherwise, it opens it again. Example: if order service tries to call payment service and it consistently times out, the circuit breaker opens. Any subsequent calls from order service to payment service would immediately fail or use a cached fallback value rather than waiting for a timeout, giving payment service time to recover without overwhelming it. Benefits: prevents cascading failures, provides immediate feedback to the calling service, and gives the failing service time to recover. Bulkhead pattern. Concept. Isolates elements of an application into separate pools, preventing a failure in one area from sinking the entire system. It's like the watertight compartments, bulkheads, in a ship. If one compartment floods, the others remain sealed, preventing the entire ship from sinking. How it works. Resources, like connection pools, thread pools, or memory, are partitioned for different services or types of requests. If one service starts experiencing issues and exhausts its allocated resources, it won't consume resources dedicated to other services. Example: order service communicating with payment service might use a different thread pool than order service communicating with inventory service. If payment service becomes slow and exhausts its thread pool, calls to inventory service can continue unaffected. Benefits: limits the blast radius of failures, preserves overall system functionality, and ensures critical services remain responsive even when others are struggling. Other important resilience patterns include retries with exponential backoff, retry a failed call after increasing wait times, timeouts, don't wait forever for a response, and fallbacks, provide a default or cached response if a service is unavailable. Implementing these patterns is crucial for building robust microservices. 6.4 Containerization and Orchestration. Introduction to Docker and Kubernetes. The rise of microservices has been inextricably linked with the explosion of containerization and container orchestration technologies. These technologies provide the ideal environment for packaging, deploying, and managing hundreds or thousands of independent services. Containerization. Introduction to Docker. The problem: it works on my machine. Software often has dependencies specific to its environment, libraries, configurations, operating system versions. When moving an application from a developer's laptop to a testing server to production, environment inconsistencies often lead to problems. The solution: containers. A container packages an application and all its dependencies, code, runtime, system tools, libraries, settings, into a single, lightweight, isolated unit. This unit can then run consistently across any environment: your laptop, a test server, a cloud server that has a container runtime. Docker, the most popular containerization technology. Docker allows developers to package their applications into lightweight, portable containers. Benefits for microservices: portability. Containers run consistently anywhere, simplifying deployment pipelines. Isolation. Each service runs in its own isolated container, preventing conflicts between dependencies. Lightweight. Containers share the host OS kernel, making them much lighter and faster to start than traditional virtual machines, VMS. Efficiency. More services can run on the same hardware. Container orchestration. Introduction to Kubernetes. The problem: running a few containers manually is fine. Running hundreds or thousands of containers across many servers, managing their deployment, scaling, networking, and health checks is practically impossible without automation. The solution: container orchestration. Orchestration platforms automate the deployment, management, scaling, and networking of containers. Kubernetes, the de facto standard for container orchestration. Kubernetes, often abbreviated as K8s, is an open-source platform designed to automate deploying, scaling, and operating application containers. Key capabilities of Kubernetes: simplified. Automated deployment and rollouts. Automates deploying new versions of applications and rolling back if something goes wrong. Self-healing. Automatically restarts failed containers, replaces unhealthy ones, and kills containers that don't respond to health checks. Service discovery and load balancing. Integrates service discovery and can distribute traffic across service instances. Storage orchestration. Mounts storage systems, local storage, cloud providers to containers. Configuration management. Helps manage sensitive information secrets and application configuration. Resource management. Allocates CPU and memory resources to ensure efficient usage. Horizontal scaling. Automatically scales services up or down based on load. Benefits for microservices: operational simplicity. Automates much of the operational burden of managing a distributed system. High availability ensures services are always running and restarts them on failure. Scalability allows services to scale dynamically to meet demand. Consistent environments provides identical environments for dev, test, and production. While this book doesn't dive deep into the operational complexities of Docker or Kubernetes, understanding their crucial role in enabling a modern microservices architecture is essential. They provide the automated fabric upon which the hundreds of independent services can run, communicate, and scale efficiently. Having built our services and provided a robust infrastructure, the next critical step is to understand what's happening within our distributed system. Chapter 7 will turn our attention to observability, logging, monitoring, and tracing, which are vital for understanding and debugging complex microservices. Chapter 7. Observability, knowing what your services are doing. In a monolithic application, when something goes wrong, you often have a single application log file, and perhaps a few system metrics to examine. It's like trying to find a problem in a single, well-lit room. In a microservices architecture, however, traditional monitoring approaches quickly fall short. With dozens or hundreds of independently running services communicating asynchronously across a network, a single request can fan out across many different components. When a problem arises, diagnosing it becomes akin to finding a needle in a haystack spread across a sprawling, dimly lit city. This is where observability becomes not just important, but absolutely essential. Observability refers to the ability to infer the internal state of a system by examining its external outputs. In the context of microservices, this means collecting, correlating, and analyzing various data points to understand system health, performance, and behavior. It's about being able to answer questions like, why is the order confirmation page slow for some users? Are all instances of the payment service healthy? What caused the recent spike in errors for the shipping service? Did a specific user's request successfully complete its journey through all the services? Observability is typically broken down into 3 pillars: logging, monitoring, and distributed tracing. 7.1 The importance of observability in distributed systems. Why is observability so critical for microservices? Complexity management. Microservices introduce inherent complexity due to their distributed nature, asynchronous communication, and independent deployments. Observability provides the tools to manage this complexity. Faster problem diagnosis. When a customer complains about an issue, observability allows operations teams and developers to quickly pinpoint which service or component is causing the problem. Performance optimization. By monitoring the performance of individual services and the entire system, bottlenecks can be identified and optimized. Proactive issue detection. Early warning signs of potential problems, e.g., rising error rates, increasing latency, can be detected before they impact users. Understanding system behavior provides insights into how services truly interact in production, uncover unexpected dependencies, and validate design assumptions. Trust and confidence. Knowing that you can understand the system's behavior increases confidence in deploying changes and scaling the architecture. Without robust observability, a microservices architecture can quickly become a black box, making it incredibly difficult to troubleshoot, maintain, or evolve. 7.2 Logging. Centralized log aggregation. Logs are the foundation of observability. Every service, whether it's a web application, a database, or a message broker, produces logs detailing its activities, errors, and state changes. In a microservices system, these logs are scattered across many different machines and containers. Trying to SSH into hundreds of machines to collect logs for a single transaction is clearly impractical. This is why centralized log aggregation is paramount. How it works. Structured logging. Services should generate logs in a structured, machine-readable format, such as JSON. This makes it easy to parse, query, and analyze the logs later. Key information like timestamps, log levels, info, warning, error, service name, and unique correlation IDs, see distributed tracing, should always be included. Example, instead of order placed successfully, use, timestamp at service, order service, level, info, message, order placed, ordered. XYZ, userid. User 456, traced, ABC 789. Log shippers agents. Lightweight agents, e.g., Filebeat, Fluentd, Logstash, Vector, run on each service host or within each container. These agents collect logs from specified locations, e.g., file paths, standard output. Centralized log store. The collected logs are then shipped to a centralized logging system. This system parses, indexes, and stores the logs, making them searchable and analyzable. Popular choices include Elk Stack, Elasticsearch for storage and indexing, Logstash for collection and parsing, Kibana for visualization and querying. Splunk, Datadog Logs, Sumo Logic, Grafana Loki. Benefits: single pane of glass. All logs are accessible from one place, simplifying searching and analysis. Correlation allows you to trace a request across multiple services by searching for a common correlation ID. Alerting and monitoring. Logs can be used to set up alerts for specific error patterns or security events. Auditing and compliance. Provides a trail of system activities for security audits or regulatory compliance. 7.3 Monitoring, metrics and dashboards. While logs provide detailed forensic information about events, monitoring focuses on collecting numeric data, metrics, about the system's performance and health. Metrics are aggregate values collected over time, giving you a quantitative view of what's happening. Types of metrics: system metrics, CPU utilization, memory usage, disk I/O, network traffic. Application metrics: request rates, error rates, latency, throughput, queue depths, open connections. Business metrics: number of orders placed, active users, payment success rates. These connect system performance directly to business outcomes. How it works. Instrumentation. Services are instrumented by adding code that exposes metrics. This can be done via client libraries or by leveraging built-in frameworks. Collectors. Monitoring agents or dedicated collectors, e.g., Prometheus, Telegraph, StatsD scrape, or push metrics from services at regular intervals. Time series database. Metrics are stored in specialized databases optimized for time series data, e.g., Prometheus, InfluxDB, Graphite. Dashboards and visualization. Tools like Grafana or Kibana connect to the time series database to create interactive dashboards that visualize key metrics. Benefits: real-time health check, provides immediate insight into the health and performance of services. Trend analysis, identify patterns, historical performance, and seasonal variations. Proactive alerts, set thresholds on metrics to trigger alerts when anomalies occur, enabling proactive intervention. Capacity planning, understand resource utilization and determine when to scale up or down. Good monitoring involves tracking the golden signals. Latency, how long requests take. Traffic, how much demand is being placed on the service. Errors, rate of failed requests. And saturation, how full your service is. 7.4 Distributed tracing, following requests across services. In a microservices architecture, a single user request can initiate a cascade of calls across multiple services, often through synchronous HTTP requests and asynchronous message queues. When something goes wrong, identifying which service in the chain caused the problem, or where the latency originated, is incredibly difficult with just logs and metrics. Distributed tracing solves this problem by tracking a single request as it weaves its way through all the services it touches. How it works. Trace ID and span ID. When a request first enters the system, e.g., via the API gateway, a unique trace ID is generated. Each operation within a service, e.g., processing an API call, making a database query, sending a message, is called a span. Each span is given a unique span ID and also references its parent span ID. Context propagation. The crucial part is that the trace ID and span ID and parent span ID are propagated across all calls between services. When Service A calls Service B, Service A includes the trace ID and its own span ID in the request to Service B. Service B then starts its own span, linking it as a child of Service A's span. Trace collection. All services send their span data to a centralized trace collector, e.g., Jaeger, Zipkin, OpenTelemetry. Visualization. The trace collector reconstructs the entire request flow as a visual graph, showing the sequence of calls, the time taken by each span, and any errors encountered. Benefits: end-to-end visibility. See the complete journey of a request through the entire distributed system. Performance bottleneck identification. Easily spot which service or operation is causing latency within a complex transaction. Root cause analysis. Trace an error back to its origin service. Understanding dependencies. Discover hidden service dependencies and communication paths. Optimizing resource usage. Pinpoint inefficient operations that consume excessive resources. Distributed tracing is one of the most powerful tools for debugging and optimizing complex microservices. It complements logging and monitoring by providing a bird's-eye view of individual requests, showing how all the pieces of the puzzle fit together to serve a user. 7.5 Alerting strategies. Observability is only truly effective if it leads to action. Alerting is the process of notifying relevant personnel when potential issues or anomalies are detected based on logs, metrics, or traces. Key principles for effective alerting: actionable. Every alert should represent a situation that requires human intervention or investigation. Avoid noisy alerts that trigger frequently but don't indicate a real problem, alert fatigue. Meaningful thresholds. Set thresholds based on the actual impact on users or business goals, e.g., latency greater than 500 ms, error rate above 1% for 5 minutes. Clear context. Alerts should provide enough information for the recipient to quickly understand the problem. What service, what metric, what threshold was crossed, and links to relevant dashboards or logs. Targeted delivery. Route alerts to the right team or individual, e.g., PagerDuty, Slack, email, based on the nature of the issue. Balance precision and recall. Aim for alerts that are highly precise, rarely false positives, and have high recall, rarely miss real problems. Alert on symptoms, not causes. Instead of alerting on CPU usage directly, alert on user-facing symptoms like service response time has increased. CPU usage might be a cause, but slow response time is the symptom impacting users. Implementing a robust observability strategy with centralized logging, comprehensive monitoring, end-to-end tracing, and actionable alerts is a non-negotiable requirement for anyone embarking on a microservices journey. It's what transforms a collection of independent services into a manageable and reliable system. But even with the best visibility, ensuring these services are safe and performant requires proper testing and security measures. Topics we'll explore in the next chapter. Chapter 8, Testing and Security in a Microservices Landscape. Building a microservices architecture is a complex undertaking, and ensuring its correctness, reliability, and safety is paramount. In a monolithic application, testing strategies often involve large, end-to-end integration tests that cover most functionalities. Security is typically applied at the application perimeter and potentially at the database level. However, the distributed nature of microservices introduces new complexities and challenges for both testing and security. Each service is an independent deployable unit, potentially developed by different teams, using different technologies and communicating over networks. This chapter will delve into how testing strategies must evolve to support microservices, emphasizing a shift-left approach and the importance of contract testing. We will also explore the unique security considerations that arise in a distributed environment, covering authentication, authorization, and secure inter-service communication. 8.1 Testing Strategies. Unit, integration, component, end-to-end, contract testing. In the world of microservices, the traditional testing pyramid still applies, but its emphasis shifts. The goal is to maximize automated testing at lower, faster levels, while acknowledging the diminished role and increased cost of high-level, slow, end-to-end tests. The testing pyramid for microservices. The testing pyramid suggests that you should have many unit tests. These are the smallest, fastest, and cheapest tests. They test individual functions, methods, or classes in isolation. They ensure a specific piece of code behaves as expected without any external dependencies. These should form the vast majority of your test suite. Fewer integration tests. These tests verify that different modules or services integrate and work together correctly. In a microservices context, an integration test might involve testing a microservice against its actual database or against a mock test version of an external dependency. Even fewer end-to-end tests. These tests simulate a complete user journey through the entire system, from the user interface down to all involved backend services and databases. They are slow, brittle, and expensive to maintain in a distributed system. Evolving testing strategies for microservices. Unit tests, the foundation. Focus, core business logic within a single microservice. Goal, ensure internal components work as expected in isolation. Benefit, fast feedback helps catch bugs early. Component tests, service-level integration tests. Focus, a single microservice including its external dependencies, e.g., its database caching layer. These dependencies are typically real instances, but the tests often run in an isolated environment. Goal, verify the microservice correctly integrates with its direct data stores and internal infrastructure. Benefit, provides confidence that the service works correctly within its own boundaries without involving other microservices. Faster than end-to-end tests. Contract testing, crucial for microservices. The problem, services communicate via APIs. If a service, the provider, changes its API contract without informing its consumers, it can break the consuming services unexpectedly. This creates tight coupling. The solution, contract testing ensures that the consumer service and the provider service agree on the format and behavior of their shared API. Consumer-driven contract, CDC, testing, the more common and powerful approach. The consumer defines its expectations of the provider's API. These expectations, the contract, are then provided to the provider. The provider runs tests against this contract to ensure it fulfills the consumer's expectations. If the provider makes a change that breaks the contract, its own tests will fail, preventing a breaking change from being deployed. Tools, packed Spring Cloud Contract. Benefits, early detection of breaking changes. Catches integration issues long before end-to-end testing. Enables independent deployment. Services can be deployed independently, knowing their contracts with others are maintained. Reduces E2E test needs. Diminishes the need for complex, brittle end-to-end tests, as inter-service communication is verified at a lower level. End-to-end E2E tests minimize where possible. Focus, a complete business flow across multiple microservices, often involving a UI. Goal, verify that the entire system works as a whole from a user's perspective. Challenges in microservices, complexity. Orchestrating multiple services and their dependencies is challenging. Flakiness, network latency, service unavailability, and test environment variability can lead to unreliable test results. Cost and speed, very slow to run and expensive to maintain. Recommendation, use E2E tests sparingly, focusing only on critical business flows that cannot be adequately covered by lower-level tests. Treat them as a final health check rather than a primary bug-finding tool. The ideal microservice testing strategy emphasizes unit and component tests within each service, complemented by robust contract testing to ensure seamless communication between services. This approach pushes testing left in the development lifecycle, finding issues earlier and faster. 8.2 Security in a distributed system. Security in a microservices environment is fundamentally different from a monolithic application. Instead of protecting a single perimeter, you now have many individual services, each with its own attack surface, communicating over a potentially insecure network. This requires a multi-layered, defense-in-depth approach. Authentication and authorization in distributed systems. Authentication, who are you? External clients. For user-facing applications, web, mobile, users typically authenticate with an identity provider service, like an auth service. This service issues a token, most commonly a JSON Web Token, or JWT, containing information about the authenticated user and their permissions. API Gateway's role. The API Gateway is the ideal place to handle initial authentication. It validates the incoming token, ensuring the user is who they claim to be. If the token is valid, the gateway can pass user information, e.g., user ID, roles as claims in the token, or as headers to the downstream microservices. This means internal services don't need to re-authenticate the user. Internal service-to-service, microservices often need to call each other. These calls also need to be authenticated. Shared secrets. Each service has a secret key to authenticate to another. This can be complex to manage at scale. Service mesh, a powerful solution discussed briefly in Chapter 6 that can provide mutual TLS, MTLS for all service-to-service communication, ensuring that only trusted services can communicate. Each service authenticates others through certificates. JWTs for service accounts. Using JWTs issued by an internal identity provider for service accounts, allowing services to authenticate to each other. Authorization. What are you allowed to do? External clients. Once authenticated, the API gateway or initial microservice can perform coarse-grained authorization based on the user's roles or permissions embedded in their token. E.g., is this user an admin? Fine-grained authorization at service level. Each microservice is responsible for its own fine-grained authorization. For example, the order service must check if the authenticated user is allowed to view or modify that specific order. This is because each service owns its data and business logic. It applies its own rules based on user identity, roles, and the specific resource being accessed. Policy-based authorization. Rather than hard-coding authorization rules in every service, a specialized authorization service can be used. Services can query this service or use policies, e.g., using OPA Open Policy Agent to make real-time authorization decisions. Securing service-to-service communication. Since microservices communicate over a network, protecting this communication is crucial to prevent eavesdropping, tampering, and impersonation. Encryption. Using transport layer security, TLS/SSL, for all inter-service communication, both synchronous REST RPC and asynchronous message queues, is fundamental. This encrypts data in transit, making it difficult for attackers to intercept and read sensitive information. Mutual TLS, MTLS. For higher security, especially in internal networks, mutual TLS can be implemented. Unlike standard TLS, where only the client verifies the server's identity, MTLS requires both the client and the server to verify each other's digital certificates. This ensures that only authenticated and authorized services can communicate. Service meshes often provide MTLS out of the box. Network segmentation. Implement network segmentation, e.g., using virtual private clouds, VPCs, or subnets to restrict traffic flow between services. This limits the blast radius of a security breach. Services that don't need to talk to each other should not be allowed to. Least privilege. Each service should run with the minimum necessary permissions. If a service only needs to read from a specific database table, it should not have write access. Secrets management. Sensitive information like database credentials, API keys, and private keys should never be hard-coded in application code. Use a secure secrets management solution, e.g., HashiCorp Vault, AWS Secrets Manager, Kubernetes Secrets, to inject these values at runtime. Regular audits and scanning. Regularly scan container images for known vulnerabilities, perform security audits of your code, and conduct penetration testing to identify weaknesses before attackers do. Securing a microservices architecture is a continuous process that requires vigilance, robust tooling, and a security-first mindset from all teams. It's not a one-time setup, but an ongoing commitment to protecting your distributed system. With our services designed, infrastructure built, and robust testing and security measures in place, the next logical step is to explore how to get these services into production, keep them running smoothly, and scale them to meet demand. This brings us to the realm of deployment, operations, and scaling. Chapter 9. Deployment, Operations, and Scaling Microservices. Building microservices is one thing. Reliably deploying them, operating them efficiently, and scaling them to meet fluctuating demand is another. In a monolithic world, deployments typically occurred less frequently and often involved downtime. Operations focused on server health and a single application instance. Scaling usually meant replacing a server with a bigger one, or perhaps running a few identical copies behind a load balancer. In microservices, these activities undergo a significant transformation. The goal is continuous, automated delivery with zero downtime, robust operational practices for a distributed system, and granular scaling capabilities. This chapter will explore the essential practices and technologies that enable these highly dynamic environments. 9.1 Continuous Integration and Continuous Delivery, CI/CD, Pipelines. The ability to deploy each microservice independently means that continuous integration, CI, and continuous delivery, CD, become not just good practices, but a foundational necessity. CI/CD pipelines automate the process of building, testing, and deploying software, enabling rapid and reliable releases. Continuous integration, CI. CI is a development practice where developers frequently integrate their code changes into a shared main branch, typically multiple times a day. Each integration is verified by an automated build and automated tests. How it works in microservices. Version control. Each microservice has its own repository in a version control system, e.g., Git. Automated build. When a developer commits code to a microservices repository, a CI server, e.g., Jenkins, GitLab CI/CD, Azure DevOps, GitHub Actions, automatically triggers a build process. This compiles the code, performs static code analysis, and creates release artifacts, e.g., a Docker image. Automated unit and component tests. The build process includes running all unit and component tests for that specific microservice. If any tests fail, the build fails, and the developer is immediately notified. Benefits: early bug detection. Integration issues are caught as soon as possible. Faster feedback. Developers receive immediate feedback on their code changes. Improved code quality. Constant testing encourages better coding practices. Reduced integration headaches. Prevents large, painful integration hell at the end of a development cycle. Continuous delivery, CD. CD builds on CI by ensuring that changes can be released to production at any time. Every commit that passes the CI pipeline is potentially releasable. How it works in microservices. Automated deployment to lower environments. After successful CI, build, and tests pass, the CD pipeline automatically deploys the microservice to a staging, quality assurance, QA, or pre-production environment. Automated acceptance tests. Further automated tests, e.g., integration tests, contract tests, basic end-to-end tests, are run against the deployed service in these environments. Manual approval gates optional. Some organizations might still have manual approval steps before deployment to production, especially for critical systems. One-click or automated production deployment. Once all automated and manual checks pass, the service can be deployed to production with a single click or fully automatically. Benefits: rapid releases. More frequent releases mean new features reach users faster. Reduced risk. Smaller, more frequent deployments are less risky than large, infrequent, big bang deployments. Reliability. The automated pipeline reduces human error. Improved collaboration. Fosters a culture of collaboration between development and operations. The ultimate goal of CD is continuous deployment, where every change that passes all automated tests is automatically deployed to production without human intervention. This is the zenith of agility and is increasingly adopted in mature microservices environments. 9.2 Automated deployments. Blue-green, canary releases. Maintaining zero downtime during deployments is paramount for highly available applications. Microservices facilitate advanced deployment strategies that minimize risk and impact on users. Blue-green deployments. Concept: you have two identical production environments. Blue, the current live version, and green, the new version being deployed. How it works. The blue environment is currently serving all live traffic. The new version of the application or specific microservice is deployed to the green environment. Thorough testing is performed on the green environment while blue remains live. Once confidence is high, the load balancer is switched to direct all incoming traffic from blue to green. This switch is nearly instantaneous. Blue is kept as a fallback for a period. If any issues arise with green, traffic can be immediately reverted to blue. Benefits: zero downtime, no downtime for users during deployment. Instant rollback. Fast and low-risk rollback to the previous version in case of issues. Safe testing. New version can be thoroughly tested in a production-like environment before going live. Cons: requires double the infrastructure capacity, which can be expensive for very large systems. Canary releases. Concept: a new version of an application. The canary is gradually rolled out to a small subset of users, observed for performance and errors, and then progressively rolled out to the rest of the user base. Analogy: named after the canaries used in coal mines to detect toxic gases. If the canary stopped singing, miners knew it was unsafe. How it works: a new version of a microservice is deployed alongside the existing stable version. A small percentage, e.g., 1 to 5% of live user traffic is routed to the new canary version. Metrics and logs from the canary are meticulously monitored for errors, performance degradation, or unexpected behavior. If the canary looks healthy, the traffic is gradually increased to the new version, e.g., 10%, then 25%, 50%, 100%. If issues are detected, traffic is immediately routed back to the stable version, and the canary is rolled back. Benefits: reduced risk. Issues impact only a small subset of users initially. Real user testing tests the new version with actual live traffic patterns. Easy rollback. Quick traffic redirection to the old version if problems arise. Cons: requires sophisticated traffic routing capabilities, often handled by API gateways or service meshes. Robust monitoring, and automated rollback mechanisms. These deployment strategies, facilitated by container orchestration platforms like Kubernetes, embody the agility and resilience inherent in microservices. 9.3. Managing infrastructure as code. As microservices environments become more complex, manual provisioning and configuration of infrastructure. Servers, networks, databases, load balancers are error-prone, slow, and non-repeatable. Infrastructure as code, ISC, addresses this by managing and provisioning infrastructure using definition files, typically in a version control system, rather than manual processes. Concept: treat infrastructure configuration files the same way you treat application code. How it works: define infrastructure. Describe your infrastructure using declarative configuration languages, e.g., Terraform, CloudFormation, Ansible, Kubernetes YAML files. Version control. Store these configuration files in Git alongside your application code. Automated provisioning. Use ISC tools to automatically provision and update infrastructure in cloud environments or on-premises. Benefits: consistency and repeatability. Ensures identical environments across development, testing, and production. Eliminates "it works on my machine" for infrastructure. Speed and agility. Automated provisioning is much faster than manual setup. Reduces human error. Automated processes minimize the risk of configuration drift and misconfigurations. Version control and auditability. Changes to infrastructure are tracked and auditable, just like code changes. Disaster recovery. Entire environments can be rebuilt quickly from code. ISC is critical for managing the dynamic and distributed infrastructure required by microservices, making it possible to create, modify, and tear down environments on demand. 9.4 Scaling strategies for individual services. One of the primary drivers for adopting microservices is their ability to scale independently. Unlike a monolith where the entire application must be scaled, microservices allow you to scale only the components that are experiencing increased load. There are several ways to scale a service: horizontal scaling, adding more instances; concept, adding more copies instances of a service to distribute the load. This is the most common and preferred method for microservices. How it works: when CPU utilization or request queue length for a service reaches a threshold, the container orchestration platform, e.g., Kubernetes, automatically spins up new instances of that service and registers them with the load balancer. Benefits: highly elastic, cost-effective, can scale down when demand decreases, and improves resilience. If one instance fails, others can take over. Prerequisites. Services must be stateless or managed state externally to allow requests to be routed to any instance. Vertical scaling, adding more resources. Concept. Increasing the resources, CPU, RAM of an existing service instance. How it works. Configuring the hosting environment, e.g., VM, container, to allocate more power to the service. Benefits. Simpler to implement than horizontal scaling initially. Cons. Has a ceiling, you can only go so big, less fault-tolerant. If the single large instance fails, the service is down, and often more expensive linearly than horizontal scaling. Generally less favored for microservices. Database scaling, horizontal partitioning, sharding, distributing data and load across multiple database instances. Each instance handles a subset of the data. Read replicas. Creating read-only copies of a database to serve read-heavy workloads, offloading the primary database. Caching. Using in-memory caches, e.g., RIDIs, memcached, to reduce the load on databases for frequently accessed data. Eventual consistency as a scaling tool. While discussed before, embracing eventual consistency allows for higher throughput and scalability. By not requiring immediate consistency across all services, you avoid distributed transactions that can be performance bottlenecks. This enables services to process requests independently and asynchronously. 9.5 Handling failures gracefully. Chaos engineering briefly. Even with the best planning, monitoring, and scaling strategies, failures will occur in a distributed system. The true measure of a robust microservices architecture is not whether it has failures, but how it recovers from them. Design for failure. Assume services will fail, networks will be unreliable, and dependencies will be unresponsive. Build services with resilience patterns, circuit breakers, timeouts, retries, bulkheads as covered in Chapter 6 from the outset. Automated recovery. Implement automated self-healing mechanisms where possible, e.g., Kubernetes restarting failed pods, message queues handling retries. Chaos engineering. An emerging discipline focused on intentionally injecting failures into a production system to find weaknesses before they cause outages. Concept. Run experiments in production to reveal potential failures, e.g., randomly terminating instances, introducing network latency, simulating database outages. Observing how the system reacts helps identify vulnerabilities and build more resilient systems. Benefits. Builds confidence in the system's resilience, discovers hidden weaknesses, and encourages teams to prepare for real-world failures. Deployment, operations, and scaling for microservices represent a shift towards automation, resilience, and a deep understanding of distributed systems. Leveraging CI/CD, advanced deployment strategies, infrastructure as code, and thoughtful scaling allows organizations to achieve the promised agility and reliability of microservices. Finally, having explored the technical aspects, it's time to step back and reflect on the broader implications of adopting microservices. We'll examine the organizational impact, migration strategies, common pitfalls, and when microservices might not be the right choice. This will bring us to our concluding thoughts in Chapter 10. Chapter 10. Adopting microservices, challenges, rewards, and the road ahead. Throughout this book, we've journeyed from the monolithic past to the distributed present, exploring the fundamental concepts, design principles, communication patterns, data management strategies, infrastructure requirements, and operational best practices for microservice architectures. We've seen how they offer compelling advantages in terms of scalability, resilience, independent deployability, and technological flexibility. However, adopting microservices is no trivial undertaking. It represents a significant shift that goes beyond just changing technology. It often requires a fundamental rethinking of organizational structure, development processes, and operational mindsets. In this final chapter, we'll summarize the key considerations, address common challenges, discuss proven migration strategies, and provide crucial advice on when not to use microservices. Finally, we'll gaze into the future of software architecture, offering some concluding thoughts and next steps for your own journey. 10.1 Organizational Impact. Conway's Law and Cross-Functional Teams. Perhaps one of the most profound impacts of microservices is on an organization's structure. This is elegantly captured by Conway's Law, which states, organizations which design systems are constrained to produce designs which are copies of the communication structures of these organizations. The monolith and functional teams. In a monolithic environment, organizations often structure themselves into functional teams. A front-end team, a back-end team, a database team, and a QA team. When a new feature is developed, it flows through these silos, requiring handoffs and coordination that can lead to delays and miscommunications. This structure inevitably leads to, or at least reinforces, a monolithic system that mirrors these silos. Microservices and cross-functional teams. Microservices, by design, are independent, autonomous services. To truly leverage this independence, organizations must adopt cross-functional teams, also known as two-pizza teams, small enough to be fed by two pizzas. Composition. Each team owns one or more microservices end-to-end, meaning they are responsible for all aspects: design, development, testing, deployment, and ongoing operations. Such a team typically includes developers, testers, and operations specialists, or site reliability engineers. Autonomy. These teams are largely autonomous within a defined strategic direction, allowing them to make rapid decisions and deploy updates without extensive coordination with other teams. Benefits: increased team ownership, faster decision-making, reduced handoffs, improved quality, and a you-build-it, you-run-it culture. The challenge: transitioning to such an organizational structure can be difficult. It requires breaking down existing silos, empowering teams with greater responsibility, and fostering new skill sets. This organizational change is often more challenging than the technical changes themselves. 10.2 Migration Strategies. The Strangler Fig Pattern. For most organizations, adopting microservices isn't about starting from a blank slate. It's about transforming an existing, often critical, monolithic application. Attempting a big bang rewrite, stopping all development on the monolith, and rebuilding everything from scratch is historically fraught with failure. These projects rarely finish, often failing due to complexity, scope creep, and the inability to deliver value during the lengthy rewrite process. A much safer and more effective approach is the Strangler Fig Pattern. Concept: inspired by the Strangler fig tree, which starts as a small vine on a host tree, slowly grows, and eventually envelops and replaces the host. You create new microservices around the existing monolith, gradually replacing its functionality piece by piece. How it works: identify a seam, find a distinct, independent business capability within the monolith that can be extracted into a new, separate microservice. Build the new service. Develop the new microservice with its own database and API, embodying all the microservice principles. Divert traffic. Gradually redirect traffic for that specific functionality from the monolith to the new microservice. This often involves using an API gateway or a reverse proxy. Remove old code. Once the new service is fully functional and stable, and all traffic is diverted, the corresponding functionality in the monolith can be deprecated and eventually removed. Benefits: reduced risk. Changes are made incrementally, minimizing disruption. Continuous value delivery. New features or improvements can be rolled out even during the migration process. Learning opportunity. Teams gain experience with microservices technology and culture in a controlled manner. Avoids big bang, no need for a lengthy, all-or-nothing rewrite. Example: Speedy Ship. If Speedy Ship's monolithic application handles both order processing and invoicing, they might start by extracting the invoicing service. All new invoicing requests are routed to the new service. Over time, historical invoicing data could be migrated, and the invoicing module in the monolith would be removed. The Strangler Fig Pattern is a pragmatic and proven approach for safely transitioning from a monolith to a microservices architecture. 10.3 Common Challenges and how to overcome them. While the rewards of microservices are significant, so are the challenges. Awareness and proactive planning are key. Increased operational complexity. Challenge: managing dozens or hundreds of services is inherently more complex than one monolith. There are more components to monitor, more deployments to coordinate, and more potential points of failure. Overcome: invest heavily in automation, CI/CD. infrastructure as code, robust observability, logging, metrics, tracing, and container orchestration platforms, Kubernetes. Embrace a DevOps culture where operations is deeply integrated into development. Latency and network overhead. Challenge: communication between services happens over a network, introducing latency and the risk of network failures. Overcome: minimize chatty synchronous communication, prioritize asynchronous communication, events message queues, co-locate related services where possible, and design for failure with resilience patterns, circuit breakers, retries, bulkheads. Distributed data management and consistency. Challenge: ensuring data consistency across multiple independent databases is difficult without ACID transactions. Overcome: embrace database per service. Understand and design for eventual consistency. Implement sagas for complex transactions, and use data replication/denormalization only when strictly necessary via events. Debugging and troubleshooting. Challenge: following a single transaction across multiple services, often with asynchronous calls, can be a nightmare. Overcome: implement comprehensive distributed tracing, centralized logging with correlation IDS, and robust monitoring dashboards. Organizational and cultural resistance. Challenge: shifting from functional teams to cross-functional teams, adopting a you build it, you run it mindset, and empowering teams can meet resistance. Overcome: executive sponsorship, clear communication, gradual change, training, and celebrating early successes. Remember Conway's Law and structure your teams to match your desired architecture. Cost challenge. Microservices can sometimes introduce higher cloud infrastructure costs, more instances, more network traffic, more database instances, and increased tooling costs. Overcome: optimize resource utilization through efficient containerization and orchestration, leverage auto-scaling, and continuously monitor cloud spending. The increase in infrastructure cost is often offset by increased development speed and team agility. 10.4 When not to use microservices. Despite their many advantages, microservices are not a universal panacea. There are situations where a monolithic architecture is a more appropriate, or at least a more pragmatic choice. Small, simple applications. For a simple application with limited functionality that is unlikely to grow significantly, the overhead of building, deploying, and operating a microservices architecture simply isn't worth the effort. A monolithic application will be faster and cheaper to develop and maintain. Early-stage startups/unproven business domains. When you are still exploring product-market fit, building a monolith allows for rapid iteration and experimentation. The focus should be on delivering features quickly, not on perfecting architecture for unknown future scale. You can always decompose later, strangler fig. Teams lacking distributed systems expertise. Microservices require significant expertise in distributed computing, DevOps, testing, and operational practices. If your team lacks these skills, investing in training and building up capabilities is essential before jumping into microservices. Starting with a monolith and gradually introducing complexity as skills grow might be more effective. Applications with tightly coupled business domains. If the core business logic of your application is fundamentally interconnected and difficult to break down into independent bounded contexts, forcing a microservices architecture will likely result in a distributed monolith, where you gain all the complexity of distributed systems without any of the benefits of true independence. Monolith first. For many new projects, a monolith-first approach is advisable. Build a well-architected monolith with clear internal modularity. This allows you to learn the business domain, prove the concept, and iterate quickly. If and when the pain points, scalability, deployment speed, team bottlenecks of the monolith become significant, then you can strategically apply microservices principles to decompose it using patterns like the strangler fig. 10.5 The future of software architecture. The journey through microservices is part of a larger, ongoing evolution in software architecture. While microservices remain a dominant paradigm, the field continues to evolve, with new patterns and technologies emerging. Serverless computing pushes the abstraction further, allowing developers to focus purely on code without managing servers or containers. Microservices can evolve into serverless functions, function as a service (FaaS). Service Mesh provides a dedicated infrastructure layer for handling service-to-service communication, traffic management, security, and observability, offloading these concerns from application code. Platform engineering focuses on building internal platforms that provide a paved road for development teams, abstracting away much of the underlying infrastructure and operational complexity, making it easier to adopt microservices and cloud-native patterns. Data mesh, an emerging paradigm for decentralized data management, moving beyond centralized data lakes to treat data as a product, owned by domain teams. The common thread through these evolutions is a continuous pursuit of agility, scalability, resilience, and developer productivity. Key takeaways and next steps. Having reached the end of our journey, here are the most important takeaways. Microservices are an architectural style, not a silver bullet. They solve complex problems but introduce new ones. It's a socio-technical transformation. Organizational structure and culture are as important as technology. Focus on the why, not just the how. Understand the business drivers and pain points that microservices aim to solve. Prioritize autonomy and loose coupling. These are the non-negotiables for success. Invest in automation, observability, and resilience. You cannot operate complex distributed systems manually. Start small, learn fast, and iterate. The strangler fig pattern is your friend. Don't start with microservices just because it's trendy. Understand your context and problems first. Where to go from here? Your learning journey has just begun. This book has provided a comprehensive, high-level overview. To delve deeper, read more, consult the further reading section, which would typically appear here for authoritative books and articles. Practice. Get hands-on experience with technologies like Docker and Kubernetes. Try building a small microservices application. Join a community. Engage with fellow practitioners in online forums, meetups, and conferences. Embrace learning. The world of software architecture is constantly evolving. Stay curious and keep learning. Microservices Demystified has aimed to provide you with the foundational knowledge to confidently embark on your microservices journey. Whether you are a developer looking to understand modern architectures, a technical lead planning a migration, or simply a curious mind, the concepts and strategies outlined here will serve as a valuable compass in the ever-evolving landscape of software development. Go forth and build amazing, resilient, and scalable systems.